All right, so I want to talk just briefly about uh, the one application that you're able to do now that you can solve differential equations in this way, and this is mixture problems. So this is kind of a family of applications that lead to some interesting results and some interesting questions that we couldn't solve without differential equations. So the book goes through some a process of building and developing the equation that describes the mixture problems. So in a mixture problem, we've got some stuff dissolved in some sort of liquid. Now the official terms are we've got some solute. Try that here. We've got some solute dissolved or mixed in a solvent. All right, so think salt dissolved in some water. Right? So that's the first thing that's happening. And what we're interested in doing is keeping track of how much solute is in this mixture. How many pounds of salt are actually in the mixture, or whatever it is we've got mixed in there. And of course it's all mixed together so we can't see it, but we would like to keep track of it. And when I say keep track of it, I mean we want to find a function, right? Find x of t, a function of t that gives the amount of solute, right? The amount of solute in the mixture at time t. Okay. Now, what makes this interesting is, of course, we are actually dealing with it in this way. We've got a tank, and into this tank is flowing our mixture, and out of this tank, right, we have some coming out as well. So we've got an input and we've got an output, and they may not be the same. You know, it may be coming in faster than it's going out. If it's going out faster than it comes in, it's a little simpler. But we're going to assume that at least there's some difference there. They could be the same. Also, there might already be some stuff in here, right? There also might be. It also might be have a certain a starting volume, right? So V of t is the volume. Now the book goes through the process, and I think it's an interesting process of how we go through the thinking through this problem and how it ultimately leads to a differential equation that we can solve. So let's walk through some of those steps to see how this works. Now the first thing we're going to do is we're going to try to come up with, let's talk about the input. All right, so let's talk about how much is coming in. Okay, so what we do is it's kind of, we've got a certain rate, r sub I, all right, and I'll include this. So this is in liters per second. A certain amount of fluid coming in, and it's already mixed, all right, and it's mixed at a concentration of C sub I. So that's remember, concentration would be basically how much of the salt, we'll just talk salt and water, how much salt divided by the total volume of the stuff you're adding, and that is in grams per liter, right? We've got 100 grams per liter of water coming in, and then we let this come in for a short amount of time but we'll call it delta t. It's a change of time, short amount of time, that many seconds. Okay. Now, the reason we write this out is because we can see that our units are going to be crossing out, and all we're left with is grams. So this little formula, rate times concentration times time, tells you how much you have coming in. Okay. This is the amount of salt that comes into the tank. All right, so that's kind of important. So using that idea, now we could have the same. Let's do it this way. Yeah, I like it this way. For the output, we have the same idea. The amount of salt coming out is the rate of stuff coming out times the concentration of stuff coming out times how long it's coming out for. Okay. And I'm going to do this because I think I can. Let me pause this. Okay, so we'll go green and red for input and output, if the superscripts don't tell you that anyway. So remember, X represents how much salt is in here, right? Total. So the change in X over this little bit of time that we let the water flow in and flow out is simply going to be the grams that are input minus the grams of salt that are output. Okay? Or approximately, we've already established this, right? R sub I, C sub I times delta T minus R sub 0, C sub 0 delta T. Okay, the stuff, how much comes in minus how much comes out. Now if we divide everything by delta T, right, it looks like some algebra. We're going to divide everything by delta T. We get delta X over delta T equals R sub I, C sub I minus R sub 0, C sub 0. Okay. And again, you don't need to memorize this. It's just, I think it's an important process to see developed so you can see where differential equations come from. All right, now we're gonna do some hand waving here, and we're gonna say, okay, now we want to take a limit as t goes to 0 here, right? That's what we do when we're ultimately finding derivatives, is we let t go to 0. The amount of time that passes goes to 0. And when we do that, as delta t goes to 0, okay, as delta t goes to 0, we have some things like continuity and differentiability that comes into play. We are led to this straight up differential equation. dx dt. Remember, x represents how much salt. Actual salt is in there. That's equal to the rate R sub I, C sub I minus R sub 0, or R sub O output, C sub O. Okay, we get a differential equation. Now what's significant about this differential equation is there are some things that are held constant. Okay, the two rates are constant. How much is coming in and how much is coming out. The concentration of the input is constant. Okay, so these are constants. Okay, the only thing that's changing is the concentration of the output, because what happens is this salt water comes into the tank and mixes with what's already there at whatever concentration it was, and so that changes the concentration coming out. Everything else is constant but that. So if we just recognize, okay, the concentration that's coming out is this. It's how much salt is in the water divided by the volume of the water. Then we can add that, let's put a little asterisk, in for C. So we end up with dx dt equals the rate coming in, the concentration coming in, minus the rate going out, times x of t over v of t. Okay, so remember, x is the unknown function. Capital V is the volume in the tank that might be changing, right? Because if the input is more than the output, then the volume's increasing, or vice versa, right? Now, we keep things fairly simple, and we're going to actually talk about this. We'll just write this. If the amount, if V sub 0 is the volume at time 0, so this is V sub 0 is how much we start with in the tank, then we can actually come up with an equation for the volume function, right? This guy right here, which is actually fairly simple. It's how much you start with plus the difference of the rate in, or the rate in minus the rate out. That's rate, right? These are rates, so this is something over time times time. And that gives us the volume, the formula for the volume, all right? And we can use that if we know the rate in and the rate out, okay? That all of that being said, this is the differential equation right there that we typically start with. We might have to do a little work to figure out what the volume is, and the volume function is, and it's given right here, right? You just need to do that. But once you get that differential equation for this tank of water, it should be solvable by, I mean, it should be a linear first order equation solvable by using an integrating factor. So hopefully that lets you see a couple things, how we develop a differential equation from basic principles, right? And this idea of letting delta t go to time is where the derivatives come in. And we end up with a differential equation that we can solve for x, which is a function that gives us how much solution is in the mixture at a given time. All right. So if we just look real quickly at at an example, suppose we have a 120 gallon tank that it contains 90 pounds of salt dissolved in 90 gallons of water. Okay, and it's a 120 gallon tank, so it's a big tank. So we're not full, I guess, is the point here. So this mixture, which is brine, right? When you mix salt with water, but this brine mixture, a brine mixture flows in that contains, so the input, let's use our fancy colors here. The input is 2 pounds per gallon. That's the concentration, right? 2 pounds per gallon. So that's the concentration in. So that's how much flows in to the tank at a rate of 4 gallons per minute. Okay, so that's how much. So 4 gallons per minute is coming in, and it is a concentration of 2 pounds per gallon of salt. All right, and then it gets in the tank, and we assume everything's mixed up, and we, all of that, and then we have our output. How much is coming out? So the rate out, remember, this is the rate out is 3 gallons per minute. So we're 4's coming in, 3's going out. So the question is, how much salt does the tank contain when it is full? So I guess this is, so we've got a 120 gallon tank. So that's our question. How much salt is in the mixture? When the tank is full. So to answer that question, we need ultimately to find the equation that gives us the amount of salt in the tank, right? So if we kind of follow our procedure, we say, okay, the change in the amount of salt, right? Remember, X is the amount of salt. is equal to the input, so the rate input times the concentration input times delta T, minus the rate output times the concentration output. Let's put a little aside here, right? What is the concentration of the output? Well, as we said, it's x over v of t. It's x of t over v of t. And we mentioned this earlier. X of t is unknown. But v of t we can figure out using our little rule right there. It's the amount we start with. So it's 90, right? Plus the rate in, which is 4, minus the rate out times t. So it's basically going to be x of t times, or over 90 plus t. And so there it is. That goes right here. So x over 90 plus t delta t, right? Now, I'll simplify this just a little bit here in a second. But there it is. There's the change in x. Now, if we divide by delta t and let delta t go to 0, we end up with our differential equation. dx dt plus 3 over 90 plus t x equals 8. Okay, right? So that being said, right, our differential equation is, let me just put this in red, right? So we added this whole delta x line and things like that so you could see how it approached. But our delta, but the equation is going to be dx dt. We've already mentioned this, right? dx dt equals the rate in times the concentration in minus the rate out times x of t over v of t, which is v. I'll leave it as v of t, x of t over v of t for simplicity, but I'm going to put a little asterisk there so that you can remember that v of t is right here, right? We've got lots of asterisks there. But that's the equation, and you can see that all that I've done to get here is put it in the form that works for using an integrating factor. Remember, we've got to have, to use an integrating factor, you've got to have your derivative plus some function of the independent variable times x or y equals some other function. Okay? So if we just kind of, that's the differential equation we want to solve. So let's keep track of that. That's the differential equation we're going to solve. So our integrating factor, actually this is rho of t, right? Rho of t equals e raised to the integral of 3 over 90 plus t dt, which is going to be e. Now if you integrate 390, you're going to get 3 ln of 90 plus t. Okay, if we actually do that integral, that's our integrating factor. We multiply, right? And I think we learned last time that we like it better like this. Cubed, right? Move that 3 up there per rules of exponents. So we're going to multiply that times the left hand side, which is dx over dt plus 3 over 90 plus tx. We've got to be real careful because now in this problem x is the function, t is the variable, not a problem, but just remember we got to be flexible with that, equals e to the ln of 90 plus t cubed, 90 plus t cubed times 8. That's the right hand side, right? Looks like we've made a mess of things, but we know that when we integrate both sides with respect to dt, right, we'll squeeze those in there. This left hand side we don't even have to bother with. We know what the integral of this left hand side is. it is simply x of t times e raised to the ln of 90 plus t cubed, right? Don't have to do any work. The right hand side, we do have to do some work, right? But it's not that bad, because if we were to simplify that right hand side, I got my integral in the wrong spot. If we were to simplify that right hand side, it's just going to boil down to 90 plus t quantity cubed, right? So I'm going to write that here. This right hand side becomes 8 times 90 plus t cubed dt, right? We can actually do that integration by substitution. Let's let u equal 90 plus t, because look, the derivative of u is simply 1. That's in the function. So that means dt equals du. So when I substitute in here, we have 8. We have the integral of u cubed dt. It works out very nicely. So this becomes 8 times u to the fourth, or 90 plus t to the fourth over 4. The 8 and the 4 are going to cancel. Plus c. 8 and the 4 cancel, leave us with a 2. So we've got x of t. Let's clean up the right hand side using rules of exponents and logs, times 90 plus t cubed equals 2 times 90 plus t to the fourth plus c. Divide everything by 90 plus t cubed so that I get x by itself. X of t is equal to 2 over 90 plus t, right? 2 over 90 plus t plus c over 90 plus t cubed, right? Now, that's a general solution because we still have c in there. In order to answer our question, we need to figure out what c is. So do we have an initial value here in this problem? The answer is yes. We started with 90 pounds of salt in 90 gallons of water. That's what it tells us there. So that means the initial condition that we have is x at time 0 is 90, right? That's how many pounds of salt we started with. So let's throw that in there and see what we end up with. I'm going to do that off screen to save a little recording space. And when we do that, we get c equals negative 90 to the fourth. All right. So we end up with, we'll put that here. C must equal negative 90 to the fourth power, like that. Okay. So we now have an equation. X of t equals 2 over 90 plus t minus 90 to the fourth over 90 plus t cubed. And now we can answer the question, how much do we have when this thing is full? Well, how long does it take to get full? Well, it starts at 90 gallons. It has 120 capacity, so it's got 30 gallons to give, right? It's got to gain 30 gallons. Look at the rates. 4 coming in, 3 going out every minute. So that means every minute it increases by 1. So it takes 30 minutes to fill up. How long to fill up? $30 minutes, right? Because 4 is coming out, 4 is going in, 3 is going out. We're gaining 1 gallon a minute. We fill up with 30 more gallons, so 30 minutes. So how much when it is full? Well, we plug 30 into our formula, right? 2 over 120 minus 90 to the fourth, 90 to the fourth over 120 to the third, and that's going to equal about 202. About 202 pounds, right? So it's a very interesting problem. Uh, we, I think it's interesting because we end up with, just think about how complicated this is. This tank, water's coming in at a certain concentration, water's going out, and it's mixing, and we're just trying to keep track of how much salt is in the water. Well, we can do that with a fairly simple, it may not look terribly simple at this point, but really the principles are fairly simple. Rate times concentration times time, that's how much salt is in there, right? All right, so that should get you started on the couple mixture problems that are assigned.